I'm Kevin. Welcome to my cave. Last time, we adapted a basic transistor current source into a common emitter amplifier and built a functioning amplifier on the breadboard. We showed how to compute the gain of this simple amplifier. This time, I'd like to show a few more basic circuits, still using our idea that a transistor adjusts the current between collector and emitter to keep the base and emitter voltage constant. We can at least see what they do, so that we can recognize them later and get a feel for why we might want to have them. So let's get started. The first circuit I'd like to take a look at is an emitter follower. Its schematic looks almost like a common emitter amplifier turned upside down. The input signal still comes in at the transistor's base. This time, though, we'll connect the collector to the power supply. We'll pull the emitter down to ground in the same way that we pulled the collector up when we built the common emitter amplifier. And we'll take the output off the emitter rather than the collector. Remember that our mental model has a little person inside the transistor, adjusting the current to keep the base emitter voltage equal to 1 diode drop. So the follower is keeping its output voltage 1 diode drop below its input. That's why it's called an emitter follower. The voltage on the emitter follows the voltage on the base. But wait! Doesn't a diode do that already? Well, sort of. Let's set up both circuits on a breadboard and see. Let me fill in the actual plus 12 supply voltage, put in actual values for the pull-down resistors, give part numbers for the diode and transistor, and try it out. Here it is on the breadboard. I have jumpers all over the place, because I plan to make modifications. You can pick up the schematic of what I actually have here from the project GitHub. There's a link in the video description. I have one scope channel looking at a sine wave from my function generator, 2 volts peak to peak. A second channel will look at the output from the diode circuit, and a third will look at the output from the transistor circuit. I'll turn on the signal generator. Well, that's a disaster. As soon as the input voltage is less than a diode drop above ground, the diode stops conducting and the transistor cuts off. That's embarrassing. Let's fix that. We could fix this problem by adding biasing networks, or simply set an offset voltage on the signal generator. But this sort of limitation is why it's common for analog circuits to run with split supplies. That way, our AC signals can oscillate around ground. So I'll move the pull-downs from ground to the negative 12 volt supply and try again. I'll move the pull-down resistors from ground to negative 12 volts. Wait a minute. That didn't seem to help at all. Both circuits are still clipping when the input is less than about 0.6 of a volt above ground. That shouldn't be. This is a simple circuit. Checked all the jumpers on the breadboard. Everything looks right.
Kevin?
Yes, dear?
Did you want to turn on the power supply?
Yes, you're right. Of course I did. I love my wife. She finds the things I lose and remembers the things I forget. Repeating what I said in the last couple of episodes, a transistor isn't a source of energy. It's a valve, not a pump. If a power supply isn't driving the collector and emitter, a transistor is just a pair of diodes. It won't amplify anything unless it's supplied with power, which I suppose is what the power supply is for. There, that's better. Both circuits are working as I expect. The outputs are following the inputs, 1 diode drop lower. So what's the point of having the transistor here? Well, my signal generator has an output impedance of 50 ohms. That's pretty close to an ideal voltage source. But what if I'm using a higher impedance source? Let me simulate that by putting a resistor in series with the input. The diode circuit is essentially a voltage divider. If you're interested, pause the video and run through Ohm's and Kirchhoff's laws to work out the gain and offset. What I expect to see is that the circuit loads the input so that the anode of the diode is oscillating around a level about 1.6 volts above the negative rail, while the cathode is oscillating around a level about a volt above the rail, with an amplitude a little under a tenth of the input signal. The transistor, on the other hand, will source enough current to keep the output voltage a diode drop below the input. The base will draw next to no current, so it will stay at the input voltage and not load the source. Let's put that resistor on the inputs and try again. I already have the input resistors on the board, so I can put them in place just by pulling the jumpers that short them out. And now we see the difference between the transistor and the diode. The transistor is continuing to follow the input, while the diode is way the heck off the screen. Let me adjust the vertical scale. What's that set to? That says it's 5 volts per division, so the diode is sitting down at about minus 11 volts. If I change the coupling to AC, I can see what kind of a signal is superimposed on that minus 11 volts. And it looks to be about 200 millivolts peak to peak. So that's not terribly useful. The transistor is obviously outperforming. So let me get rid of that diode trace. I'm done with it. There's still one more issue with this circuit, and that's the way it behaves with a large input signal under load. To see that, let's add a 1 kilo ohm resistor to ground to serve as a load on the output. With that in place, we'll crank up the voltage in steps to about 10 volts peak to peak and see what happens. I'll add a jumper to that load resistor. I'll adjust my vertical scales so that everything will fit when I increase the levels. And when I increase the voltage level, you see what the problem is. Everything is clipping at about negative 3 volts. Just can't seem to pull it down any lower than that. What's happening here is that the circuit is asymmetric. The transistor can source quite a lot of current. We need a better transistor model to say how much. But the pull-down resistor can't source very much at all. Once the output voltage hits that negative 4 volt level, the transistor is completely cut off. The pull-down resistor and the load are working as a voltage divider. We get negative 4 volts out, and that's all. It's tempting to say, just make the pull-down resistor much smaller than the load. 1% should do it, right? But look at what happens when we do. When the output is at ground, there's no signal going out. The resistor will be drawing 1.2 amperes. And this is to match a 1 kilo ohm load. A stereo power amplifier might be driving a 4 ohm load. We need a better approach. The key to the better approach is in what I just said. The circuit is asymmetrical. The transistor can source a lot of current, but the resistor can hardly sink any at all. I could make the problem go the other way by using a PNP transistor instead of an NPN. Now the transistor can sink a lot of current, but the resistor can source only a tiny amount. But what if I were to replace that pull-up resistor with an NPN follower? On the positive half of the cycle, the NPN transistor should push current into the load. On the negative half cycle, the PNP transistor should pull current out of it. This is the idea behind a circuit called a push-pull amplifier. Why don't you try to figure out for yourself what's wrong with the push-pull amplifier the way I've drawn it, while I go down to the cave and breadboard it? I have that 2-transistor circuit here on the breadboard, and when I run a signal into it, the good news is that it's not clipping at negative 3 volts. The bad news is where the signal crosses 0, you're getting these weird distortions, And if I lower the input level, down to a volt or so, the output goes away entirely. What's happening, of course, is that when the input signal is within a diode drop of ground, positive or negative, both transistors are cut off. The amplifier sources no current. Engineers have worked out a lot of ways around this problem. I'm showing one fairly simple one here. The chain of 3 resistors that you see, when there's no input, is fixing the bases of the 2 transistors at 0.6 of a volt above and below ground. That puts them just at the threshold of the active region. The 2 capacitors superimpose the AC input signal on this DC offset. The top transistor starts to conduct as soon as the input swings positive, and the bottom one starts to conduct as soon as the input swings negative. We can breadboard this version too, and look on the scope. And here's that improved circuit on the breadboard. When I turn it on, you can see that crossover distortion has largely disappeared. So adding a few extra components to keep the transistors from saturating largely calms that problem. The astute among you might be wondering, what if the component tolerances are a little off, and the zero input state puts the bases a little bit more than a diode drop from ground? Won't both transistors be conducting heavily, each one trying to hold its base emitter voltage at one diode drop? That would effectively be short-circuiting the power supply. The answer is that it doesn't happen if you choose your component values properly. I'll get into that next time with a better transistor model. I know, I keep saying that, don't I? But before we go, I want to take a quick look at one more basic circuit, the saturated switch. The saturated switch is very much like the current source that we've seen already, but without an emitter resistor. Unlike the other circuits we've looked at, this one ideally never has the transistor in the active region. If the input voltage is more than a diode drop above ground, the transistor is saturated and sinks a lot of current. If the input is less than a diode drop above ground, the transistor is cut off and the collector looks like an open circuit. The way I've drawn it here, the lamp will be on any time that the input voltage is a logic high, and off any time the input voltage is a logic low. How much current can the circuit pass? Once again, we'll need to wait until next time to see, with a better transistor model. One thing to watch for with the saturated switch is attempting to drive an inductive load, such as a motor, a relay, a solenoid, or a loudspeaker. Let me show what can happen on the breadboard. For a power supply, I'll just use a AA flashlight battery. For the inductive load, I'll use the coil of a relay that's designed for 24-volt operation. So here's that switch set up on a breadboard. I've wired up a push button to give me a logic level. I don't want to use an oscillator here, because I don't want to operate the switch repeatedly the way it's wired, and we'll see why in just a moment. I'll put the scope on the transistor collector and set it to capture a single trigger from the base. I'll push the button and release it again. And look what the scope captured. That vertical channel is set to 20 volts per division. That spike is well over 100 volts. Wow, where'd that come from? We don't need that sort of excitement. Future Kevin here. Of course, in a switching power supply, we may use a circuit very like this to generate an output voltage greater than the input. I might do some videos on switching power supplies at some point, but not today. Remember the equation relating the voltage and current through an inductor. When the transistor shuts off, the current drops suddenly, and the voltage goes through the roof. I honestly don't know what other path the voltage found to ground. My first guess is that the spike drove the transistor into avalanche conduction. Whatever it was, it can't have been too healthy. Imagine what would have happened if I were switching the full 24 volts needed to operate the relay. The spike, often called a flyback, can burn out semiconductors, strike arcs, and clobber any number of innocent electronic bystanders. Fortunately, in this case, the solution is simple. Simply connect a power diode across the load like this to drain the inductor's energy away safely. When the transistor cuts off, the current in the inductor can circulate through the diode, and the energy in the inductor is dissipated safely in the resistance of the inductor winding. I'll add that flyback diode across the relay coil. And now when I push the button, I get a nice clean transition from 0 to 1.5 volts without any bizarre 100-volt excursions. The flyback diode tames the inductor. And that's about all that I want to say about transistor switches in this particular episode. Last episode and this, we've examined 5 transistor circuits. The current source, the common emitter amplifier, the emitter follower, the push-pull amplifier, and the saturated switch. For each one, we were able to understand what the circuit does and calculate a lot about how they work. But we're struggling to characterize some of the behavior, particularly as it relates to input and output impedances. We're simply saying that the base impedance is very high, and that the collector to emitter path can move lots of current. We need to make that more quantitative. So next time, I'll update this discussion with a transistor model that's one small step better than the one we've considered so far. I'll go through the circuits we've looked at and examine the impedances and the currents that they can handle. In the meantime, stay tuned, stay safe, stay healthy, stay curious, and take care of one another. Bye!